Alrighty, well, excuse me. I am back. I've had lunch. Hopefully, you have done the same, taken measures to refresh yourself before we begin this 3-hour slog through through our office hours. So, whoa, hang on. Okay. Oh, there we go. So, hello, welcome, and are there any questions out there? Because I am here, excuse me, and I am ready to take them. I'm going to be doing some classwork on the side. I'm also, let's see. There we go. I'm going to check the old emails to see if there's any. Oh, let's see. Boom, 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 boom. Oh, let's see. Okay, awesome. Kate, would you mind explaining Lab 6 calculations for silver and chloride? Okay, let me pull these up. Lab experiment 6. Okay, so let's take a look here. I totally can. Okay. Oops. There we go. Alright, so this is Lab 6. Okay. So for original silver cations, let's see here. Okay, yes. So this is Lab 6. The data calculations, this would be data analysis. This would be 8 and 9. Okay. So let's take a look. Okay, so starting with 8. Here, this is they want us to calculate the percent of silver used. All right, and then they they actually tell us what the equation is for this. This is equal to the moles of silver chloride divided by the moles of silver nitrate, excuse me, times 100%. Oh, that is the most misshapen 100% I've ever written. There we go. So, percent of silver cations of original silver 1 cations used will be equal to the moles of silver chloride divided by the moles of silver nitrate, and I believe, if I'm not mistaken, I'm just going to shift this down for a minute. Not for a minute, actually, permanently. Photoshop's just acting a little finicky. There we go. All right. So, so this is how you calculate the percent silver, and you'll notice that you've actually already calculated both of these. Your moles of silver chloride. This you did this in step. Let's see, where was that? This was done in step 7. And then your moles of silver nitrate, you did this in step 4. So, so you simply take your value for number 7, divide by your value for number 4, multiply by 100, and that is number 8. I believe we're going to run into a similar situation with number 9. So number 9, we're calculating the percent of chloride used, and then they put a oh, interesting. They actually don't give us an equation for the percent of chloride used, but this is going to be the percent of chloride that ends up getting used will be, so let's see. Right. So our denominator will be, so the numerator here still will be moles of silver chloride, all right? Which we've already established. Gets calculated in step 7. The denominator here will be the moles of copper chloride dihydrate times 2. All right, and the reason why we need to multiply this times 2 is 1 mole of copper chloride dihydrate produces 2 moles of chloride anions, and that 2 comes from that part of the chemical equation. So if you take the moles of copper chloride dihydrate and this, you get from, I believe we calculated this, molar mass? Moles, yeah, this is step 5. And you multiply that value by 2, that's your denominator. And you multiply this by 100, and you're good to go. So, Kate, that is how you handle Lab 6, Step 7 and 8. Hopefully that gives you enough to go on. So I see you've got another question for data analysis. Oh, parts 4 and 5. Okay, so I was just about to say, so yeah, so that will give you enough to start on, but you actually have questions on how do you do step 4 and 5. So let me just do this while we're talking about Lab 6. This would be 4 and 5. Steps 4 and 5 of the data analysis. Okay, so step 4 of our data analysis is we need to calculate the moles of silver nitrate All right, and what we have is, so to get moles of silver nitrate, we recorded under our data section the mass in grams of silver nitrate. So to find the moles of silver nitrate, we need to do a unit conversion that'll convert grams of silver nitrate to moles. And this, you have to calculate your molecular weight based on the chemical equation for silver nitrate. So you do that, and when you divide your mass by your molecular weight, it will give you your moles. All right, and this mass is from the data spreadsheet. All right, step 5, I believe, will be something similar. Let's take a look at step 5. Okay, so here we need to calculate the moles of copper 2 chloride dihydrate. All right, and again, to do this, you take the mass. Oops. Mass starts with an M. Ooh. No. There we go. The mass in grams of copper 2 chloride dihydrate. And you multiply, so we need to convert from grams, right? So we put grams in the denominator for this unit conversion, moles in the numerator. And this, again, this unit conversion, you need to take, you'll find that by calculating the molecular mass. How many grams of this molecule are in 1 mole? And remember, it's 1 copper, 2 chloride atoms, and then 2 water molecules. You include that in the molecular mass. And this will equal moles of copper 2 chloride dihydrate. And again, where you get this mass is from the data spreadsheet that was posted. So this is how you get steps 4 and 5, which then you use in steps 8 and 9 of the data analysis. So Kate, hopefully that gives you some rails to run on. If it's still confusing, not making sense, circle back around, hit me with another question, but hopefully that gives you a place to start from. All right, Esther, let's see. So when calculating original moles, should the answer be rounded to a number times 10, or should it be without a 10? Excuse me. Esther. So quick question. Let's see. Okay, so here's my question to you, Esther. Okay. Carenza, when we calculate the molar mass of a compound using the periodic table... Ah! Carenza, great question. The molar mass of a compound always has units of grams per mole or AMU, because these two things, these are the same, but I will say that grams per mole is more useful. So I always just use grams per mole. Okay, yes, wondering if scientific notation... All right, So Esther, the answer to your question is okay. Susan, lab 6 in the video, when they use the test tubes to add the reactants to the supernatant, what is that supposed to reveal? I was unclear of what to look for. Okay, Susan, great question. Great question. Oops. So lab 6, supernatant. Supernatant observations. Okay. Okay, so here's the deal. So you do your reaction, right? You get your solution, you get your precipitate. Right, this is a silver chloride precipitate. And then what happens is we filter this, right? We filter this through a funnel and an Erlenmeyer flask. The solution goes through, and we're left with the precipitate on top of the filter. The precipitate on top of the filter, the filtrate through, and then what we do is we take the remaining liquid, right, the supernatant, or now we can call it the filtrate because it's been filtered. And they put it in a couple test tubes, right? And the question is, the big question that we have that we're trying to answer is this. So here's the big question. In this supernatant, or now we can call it a filtrate, is there leftover silver nitrate or copper chloride? All right. Is there leftover silver nitrate or copper chloride? And here's one way to answer that question. You put your filtrate in 2 test tubes. All right. And you add to one of them we're going to add silver nitrate. To the other one, we're going to add copper chloride. All right, I'm going to call this one number 1. I'm going to call this one number 2. All right, and we're watching. Okay, here's what we're looking for. We're looking to answer this question. Which test tube produces precipitate? All right, which test tube produces precipitate? So, for example, if test tube 1 produces precipitate, if we add silver nitrate to a test tube and we get PPT, precipitate, that means that there was leftover copper 2 chloride, because that's what the silver nitrate reacted with. For test tube number 2, if we add copper chloride to the second test tube, which we're doing, if we get a precipitate for test tube number 2, that means that there was leftover silver nitrate, because the new the new copper 2 chloride we added would react with it to make a precipitate. So, Susan, the reason why we're adding those stuff to the supernatant and seeing what we're looking for is it'll tell us which one was originally left over from the reaction. Did we have leftover copper 2 chloride? Did we have leftover silver nitrate? If we have leftover copper 2 chloride, the test tube where we added silver nitrate, that tells us that we have leftover copper. That one will produce a precipitate. If we have leftover silver nitrate, the one we had copper 2 chloride to will give us a precipitate. That's the whole point of observing the supernatant after you add, or adding those two things to the supernatant after the reaction's over. Okay, that may have been confusing. Let me know if it was, and I will I'll go over it again, but approach it from a different angle. Okay, awesome. Okay, let's see here. So, okay, Kate, It also asked for the moles in just silver and chloride. I was assuming it was asking for the mole ratio. Ah, okay, so here's the cool thing. So here's more lab 6. So if you want to find, if you have the moles of silver chloride, all right, let's just say, I'm going to make up a number. All right, let's say we have 0.283 moles of silver chloride. Which this, I totally just made this up. All right, that's not the number, that's nothing. But let's just say we have 1.2 or 0.283 moles of silver chloride. And we want to know how many moles of silver we have. Well, we're going to need a unit conversion to convert from moles of silver chloride to moles of just silver cations, right? And the ratio, this ratio, you get from the chemical equation for silver chloride. Because 1 mole of silver chloride has 1 mole of silver ions in it. So this ratio is a 1:1 ratio. Moles of silver chloride cancel. And so 0.283 moles of silver chloride will have 0.283 moles of silver cations. All right? We can do this exact same thing for chloride anions. And just like with silver cations, we base our mole-to-mole ratio on the chemical equation for silver chloride. That's how you convert between moles of silver chloride molecules and moles of chloride anions. And again, 1 mole of silver chloride molecules will have 1 mole of chloride anions. Moles of silver chloride cancel, leaving us with 0.283 moles of chloride anions. So now, okay, if we wanted to do this exact same thing, Kate kind of, let's say we had 0.512 moles of copper 2 chloride dihydrate, and we wanted to know moles of chloride. We're going to need to do a unit conversion, and that unit conversion will be based on the chemical equation for copper 2 chloride dihydrate. And here you can see that 1 mole of copper 2 chloride dihydrate contains 2 moles of chloride ions. So this is a 1:2 ratio. So here we need to double our quantity of moles. So this would be, rounded to 3 sig figs, 1 0.02 moles of chloride ions. Oh, Kate, no worries. Sorry, I just explained that, and then I just saw your second comment, where they don't actually ask you to do this, but now you know. Now you know how to do it. Okay, let's see. So Esther, you do scientific notation the way you do it on any number. Scientific notation. You are welcome, Kate. Scientific notation expresses, in scientific notation, we express the number as a product of tens with the decimal behind the first non-zero digit. So if, for example, we had 0.00894 moles, if we were to express this in scientific notation, we have to bounce this decimal place back so that it's behind the first non-zero digit. And then we'd have to multiply times 10, since we rolled it back 3, 10 to the negative third moles, for example. All right. If you got a huge number of moles, like let's say you got 4,500 moles, this would be ginormous. Again, we take the decimal, we roll it so that it's behind the first non-zero digit. So 4.5, and since we bounced it over 3 spaces, we write times 10 to the third moles. So if you are using scientific notation, you do it the same way you always do it. Okay. You could write it in scientific notation, the percents for 8 or 9. You don't have to, but you totally could if you wanted to. Okay, Carenza, let's see. For number 4 and 5 in Lab 6, how should I write my answer? Yeah, you can do it standard notation or scientific notation. Totally your choice. Let me see. For number 7, okay. Krenza, you actually do have a spreadsheet value for silver chloride. You have it in the data section. Silver chloride is the precipitate. All right, silver chloride is the precipitate, so so to find your mass, so in the data section, we have 3, is the mass of filter paper. For is, oh wait, let's see. Yeah, number 4 is the mass. Oh, it says and filtrate. It should say precipitate. 4 is the mass of the paper. Oh, I wrote filter paper. Filter paper. Plus, it says filtrate, but it should say precipitate. So the mass, oops. So the mass of silver chloride is equal to 1 minus the other, right? It's the recorded mass for number 4 minus the recorded mass for number 3. And then once you know the mass of silver chloride, you use the molecular weight. To find moles. All right, so you do have information about the about silver chloride. You can get that by taking the difference of the mass of the filter paper with the precipitate. Again, the lab calls it erroneously calls this the filtrate. It should say precipitate. Okay. Okay. So let's see. Okay, for number 7. Okay, okay. Let's see. Okay, Susan, stuck in Moleville. That's okay. My guess is many people are as well. The book, page 149, quick quiz. Here, let me grab that so I can get contextualized. All right. You said it was page 149. Okay, let's see. Quick quiz number 3. All right. It says 1 mole of sulfur atoms contains twice as many atoms as 1/2 mole. All right, let's see. Okay, so so let's look at this. So 1 mole of sulfur atoms. Let's convert this from atoms to moles. 1 mole of anything is 6.022 times 10 to the 23rd atoms. Moles cancel. So in a 1 mole sample of sulfur atoms, there are 6.022 times 10 to the 23rd atoms of sulfur. All right, now they say that it contains twice as many atoms as 1/2 mole of oxygen atoms. Well, 1/2 mole is 0.5, right? Let's convert this to atoms. Right here, moles of oxygen cancel moles of oxygen. This comes out to be, oops. Atoms of oxygen. The reason why is if you look at these two numbers, the number of sulfur atoms is twice as big. All right, but another way of thinking about this, Susan, maybe from a more conceptual perspective, here's a mathematical thing. You can see like, oh, 6.022 times 10 to the 23rd is double 3.011 times 10 to the 23rd. Another way of thinking of this, maybe from a more conceptual perspective, is saying that 1 mole of sulfur atoms is twice as much as 1/2 mole of oxygen atoms is the same thing as saying 1 dozen donuts is twice as much as 6 donuts, right? Because a dozen has 6, a dozen has 12, 6 has 6. And so one is twice the size of the other. It's the same with mole and 1/2 mole. 1 mole is just a number. It's like a dozen. So if you have 1/2 mole, you have half as much. Hopefully that makes sense. Okay. So let's see. Brianna, could I also go over some of the practice homework for chapter 6? I totally can. Okay, awesome. All right, sorry, Carinza. I'm just seeing your question about number 8 for lab 6. Let's see. Yes, Brianna, I totally can. All right, Carenza. Okay, chapter 6. Let's see, problems 35, 37, 39. All right, let's see. Determine the number of atoms of sulfur present. Oh, these are cool. Okay. So this is chapter 6. This one is number 35. They're asking us to determine the number of sulfur atoms in determine the number of sulfur atoms in step A, or part A. So first they say 10.0 grams of H2SO4. All right. Now the strategy here is going to flow like this. The way you get to atoms will always come from moles through Avogadro's number, and moles always come from grams using the molecular weight. And then this uses Avogadro's number. All right, now, so we need to calculate a molecular weight for H2SO4. All right, that's going to be our first step. Because if we set everything up, we've got 10.0 grams of H2SO4. We have to start by converting from grams of H2SO4 to moles. Next, once we know how many moles we have of H2SO4, we have one additional step here. We don't want to know how many if we used Avogadro's number right now, we would just use Avogadro's number to get molecules of H2SO4. But this problem's asking for atoms of sulfur. So we need to convert from moles of sulfuric acid to moles of just sulfur atoms. And this ratio we get from the chemical equation. 1 mole of sulfuric acid contains 1 mole of sulfur atoms. Then we convert from moles of sulfur to atoms of sulfur using Avogadro's number. All right. So we've got all of our things set up. The only thing we've got to do is figure out what our molecular weight is. And so here we've got to add up our atomic masses. We have hydrogen, we have sulfur, and oxygen. Let's see, sulfur is 32.07, oxygen is 16.00. All right, but we've got 2 hydrogens, and we have 2 hydrogens, 4 oxygens. So we need to multiply both of these. All right, so 16 times 4 is 64, plus 32.07, plus 2.02 gives us a molecular weight of 98.09. And that'll go in here. 98.09. Okay, so now that we have all these things locked and loaded, we can actually calculate how many atoms we'll have. So 10.0 grams divided by 98.09 times 1 divided by 1 times 6.022. So this is let's see if we can keep 3 sig figs. So 6.139259 times 10 to the 22. We can keep 3 of our sig figs. So that 9 will round up to a 4. So we'll have 6.14 times 10 to the 22nd atoms of sulfur. All right. I'm going to do one more of these. There's like 4 of them in this list, but I want to do one that's a little trickier. All right, so that was part A. Let's do part C. All right, part C, same story, but we're starting with 30 grams, 30.0 grams of aluminum sulfide. All right. So okay. So let's get into it. Step 1, we got to convert from grams of aluminum sulfide to moles. Step 2, we need to convert from moles of aluminum sulfide to moles of just sulfur atoms, right? And then the final step, we convert from moles of sulfur to atoms. I'm going to change color so you can see this here. All right, now, for the unit conversion between moles of sulfur and moles of aluminum sulfide, you look to the chemical equation. 1 mole of aluminum sulfide will contain 3 moles of sulfur atoms. So we put a 1 in the denominator, a 3 in the numerator. Gotcha. Yeah. And you get that, Brianna, straight out of the molecular formula. Next, we got to calculate an atomic mass with aluminum and sulfur. Right, we're dealing with 2 aluminums and 3 sulfurs. Now we saw sulfur has a atomic mass of 32.07, which we got to multiply by 3, and aluminum is at 26 point something, yeah, 26.98 times 2. So 26.98 times 2, 53.96. All right, these added together come out to be 150.17. And now we crunch our numbers. So 30 divided by 150.17 times 3 times 6.022 times 10 to the 22nd. My calculator is giving me an answer of 3.609109.7 times 10 to the 23rd. Let's see, we can keep 3 of our sig figs, and 9 is going to round up. So our final answer will be 3.60 times 10 to the 23rd atoms of sulfur. That's the only real twist to this problem, is looking at the moles of sulfur and the unit conversion between moles of the compound versus moles of atoms. All right, let's see. Okay, let's see here. So Brianna, I'm totally going to come back, circle around to do some action on 37 and 39. But let's just pause real quick so that we can answer, just because there's a couple Lab 6 questions up in the mix. Let me throw some answers to these. Okay, let's see. Okay, I got that one. Okay. Okay, there's that one. Yeah, Carinza, that's totally right. Okay, sweet. Those were the Lab 6 questions, Brianna. We can keep on rolling with Chapter 6 homework. Let's see, number 37. Let's see, determine the number of grams of sulfur present in each of the following quantities. All right. So this is determine the mass of sulfur in all right, so let's take A, for example. So for part A, they give us 301 times 10 to the 23rd molecules of S2O, disulfur monoxide. Okay, so we need to find the mass of sulfur. So the pattern here so we've got 3.01 times 10 to the 23rd molecules. We got to get this quantity into moles. And to do that, we use Avogadro's number. It's a decimal right there. To convert from molecules to moles. Next, we want to convert from moles of S2O to just moles of sulfur. And again, this unit conversion comes from just the chemical formula. 1 mole of S2O has 2 moles of sulfur atoms in it, 1 mole of S2O has 2 moles of sulfur in it. And now for the last step, we need to convert from moles of sulfur to grams, and this is just the atomic mass, because the periodic table tells us that there are 32.07 grams of sulfur in 1 mole. So molecules of S2O, cancels. Moles of S2O cancels. And moles of sulfur cancel. Now we can crunch our numbers. So we have 3.01 times 10 to the 23rd. Did I write that down right? Yes, I did. Divided by 6.022 times 10 to the 23rd times 2 times 32.07. All right, so my calculator's giving me a value of 32.0593491. All right, but we can only keep 3 sig figs because the number we multiplied with the fewest number of sig figs was our initial quantity of molecules. So you count off 1, 2, 3. Then 5 will round up. So 32.1 grams of sulfur. Grams of sulfur is the mass of sulfur inside that sample. Okay, so let's see. So that was part A. Let's do. Let me do one more of these, Brianna, and then I see there's a couple other questions popping up. Let's go ahead and do. Let's do part D of this one, and then I'll cycle out, and then I'll pop back to number 39. Part D, we start with 4.50 moles of S8. All right, well, this one's nice. We're already in moles, but we need to convert from moles of S8 to moles of just sulfur atoms. All right, when you look at the molecular formula, 1 mole of S8 has 8 moles of sulfur atoms in it, so that is our ratio here. Next, we need to convert, because we want to know what the mass of sulfur atoms are. We convert from moles of sulfur to grams of sulfur. And, this one actually ended up being shorter than I thought it would. We cancel, and now we multiply. So 4.5 times 8 times 32.07 comes out to be 1,154.52. We can keep 3 of our sig figs. So this will end up being 1,150 grams of sulfur. All right. Okay, so we'll pause. I will totally come back and do a sampling from 39. But let's go ahead and take a look at a couple of these other questions up in here. Okay, so Kate, would you mind walking through Chapter 6, practice homework number 61 and 75? I totally can. Brianna, great question. The reason why we didn't use Avogadro's number is because they gave us 4.50 moles. If they had said 4.50 molecules, then we'd have to use Avogadro's number. But because they gave it to us in moles already, we got to bypass that step, which is kind of awesome. Okay. Chapter 6, number 61 and 75. Okay, let's take a look at these. Okay, so let's write this up. So for the chemical reaction, write the conversion factor that would be needed to do each of the following conversions. All right, and so they give us a chemical reaction. Sb2 S3 plus 6HCl producing 2 SbCl3s and 3 H2S. Excuse me. Okay. All right, then they ask, write the conversion factor that would be needed to form each of the following. So for example, with A, they want to know the conversion factor to go from moles of antimony trichloride to moles of H2S. All right. So here, if we're converting from moles of antimony trichloride, that means that this is our denominator of our conversion factor. So we've got our conversion factor, and we've got to put moles of SbCl3 in the denominator. All right, and then what we're converting to, moles of H2S, that's what goes in the numerator. And then the numbers that belong there are from the balanced chemical equation. So 2 moles of SbCl3 are made with 3 moles of H2S. So that would be the conversion factor for part A. Let's look at part B. In part B, they want us to convert from moles of Sb2S3 to moles of HCl. Again, what we start with, that is the denominator for the conversion factor. So we put moles of Sb2S3 in the denominator. And we're converting 2 moles of HCl, so that goes in the numerator. And then the conversion factor comes from the balanced chemical equation. Now, whenever you don't have a coefficient in front of a number, that just means it's automatically 1. So 1 mole of Sb2S3 will react with 6 moles of HCl. All right, so C, part C, they want us to convert from moles. Oh, whoa. Moles of H2S. They want us to convert to moles of HCl. And again, our pattern continues. What we start with, what we're converting from, goes in our denominator. And then what we're converting to goes up in the numerator. And then the numbers we pull out of our chemical equation. Whoops, not 2. 3 moles of H2S are produced. Whoa. Three moles of H2S are produced from 6 moles of HCl. All right, Kate, so molar ratios are present between molecules and products between them. Yes! I couldn't have said it better myself. The molar ratios in a chemical equation are between all members. So you could do reactants to products, products to reactants. You could do reactant to reactant or product to product. Any of them, all of them are valid. And what goes in the denominator is what you're converting from. What goes into the numerator is what you're converting to. All right, so that's totally awesome. Totally awesome. Let me take a look at number, what was the other one you asked about? 75. Okay, let's see here. Ooh, cool. So this is chapter 6. Problem 75. All right, the catalytic converters is standard equipment on American automobiles. Converts carbon monoxide to carbon dioxide by the following reaction. All right, so we're given a chemical equation here. 2 molecules of carbon monoxide react with 1 molecule of oxygen to produce 2 molecules of carbon dioxide. All right, what mass of oxygen in grams is needed to react completely with 25 grams of carbon monoxide? So notice we're given, we have 25 grams of carbon monoxide, and we're asked how many grams of oxygen do we need to react completely? Well, we've got some stoichiometry to do. We've got 25.0 grams of carbon monoxide. Our first step will be to convert grams of carbon monoxide into moles. Oh, whoa. Hang on 1 second. Yikes. Holy moly. My computer got unplugged, and the one that I'm using to stream, and then it was just like, your computer's entering into battery saver mode with dangerously low battery. Okay, I'm glad our office hours didn't just shut off. That would have been a bad time. Okay, so first step, we convert from grams of carbon monoxide to moles. Next step, we need to convert from moles of carbon monoxide to moles of O2, and here we pull this ratio out of the balanced chemical equation. 1 mole of O2 reacts with 2 moles of carbon monoxide. The final step is to convert moles of oxygen to grams. All right, so we have a couple atomic masses to calculate. Carbon's atomic mass is 12.01, oxygen's is 16. So carbon monoxide will have a molecular weight of 28.01. 16 times 2 is 32. So that is the atomic mass of O2. Now, where did my phone go? Here we go. Trusty calculator. So 25 divided by 28.01 divided by 2 times 32. Oh, here, I'm actually going to write this down here. So this is 14.2806.141. Sig figs wise, we can only keep 3. So the correct answer with the correct number of sig figs will be 14.3 grams of O2. Okay, so that is number 75. Slowly working my way through. Okay, Carenza, Lab 6, number 8, getting a huge number. Seems unreasonable for a percentage. Let me take a look. There's always an off chance, though I doubt it, but it's worth double checking. Let me look at the numbers provided for the data sheet, just to make sure they're not like whack. Kate, you are welcome. Okay, here, hang on 1 second. Good news. Could you move the Animal Crossing play to a different room, please? Thank you. All right, my kid's Animal Crossing enthusiasm was starting to leak through the walls a little bit. Okay. Oops. All right, let's see here. Oh wait, hang on. Okay. Give me a second. I'm just going to double check. To make sure our numbers here aren't way off. Okay, let's see. So number 8 is the one in question. Okay, so let's see, number 8. So first, In case you're all wondering what exactly I'm doing, I am checking the numbers here. All right, number 4. Okay, let's see. Okay, here we go. Oh, whoops. Okay. Okay. All right, so number 4. So number 5, number 6. Number 7. Alright, so here's the moment of truth. Let's see. This will be percent. That one will be percent. Okay, so let's divided by and then we've got divided divided by this times 2. Okay, well, okay, so, due to the overwhelming number of questions that we've been getting with respect to like crazy huge numbers and stuff like that, for Lab 6, I just checked the numbers. So for Lab 6, this is for the percent of silver cations, the percent of chloride anions, and so I'm looking at the numbers that I calculated right now, and for both of these, given our starting values, so the for both of them, what I can say is the first digit of each percentage is in the tens place. So, like, so if you were to use scientific notation on this, it would just be times 10 to the 1. So if you're getting like a crazy small number, or a crazy huge number, you definitely have made a mistake somewhere. The first digit of both of these, both percentages, have their first digit in the tens place. So, so here's the deal. What that means is that you've messed up somewhere in your calculations. So that means you've got to go back through it and find where your error is. And sometimes this can be done by like looking at your things. I always had a hard time when I knew something was off. I had a hard time looking at my calculations written out and finding where the error was. It could be, and different learning styles, right? There are different ways of approaching things, and they'll have different effects. But I always found it easiest to find my mistakes when I just started from the beginning, just started the calculation over, and went from there. So so that's what I would recommend doing, because at this point I've like gone through how to do each step. At this point it's just it comes down to locating and troubleshooting your own calculations, which is a task that only you can complete. Okay, let's see. Where... Okay. Susan. Okay, lab 6, question 3. So let's see, real quick. Question for you, Parthana. Okay, let's see, where were we? Okay, Brianna, could you also give a practice problem about balancing chemical equations that are gonna end up with a fraction and the whole distribution thing? Okay, yes, I can totally come up with that. Okay. Okay, you did want number 3, question 3 from the part that says questions. Okay, let's see. Based on your limiting reactant, calculate the theory of silver chloride in grams. All right, so let's take a look. Lab 6, question 3. Okay, so they want, in this question, they're asking us to calculate the theoretical yield of silver chloride in grams. Okay, so Parthana, I'm not going to do this calculation for you, but I will give you the setup and let you run on those rails. All right. It's saying our stream is poor. All right, no, we're connected to the right thing. Okay, we're back. Okay. All right. So, again, I'll give you the setup. Now, whenever you're rolling with a theoretical yield, so we've got 2 reactants, right? We've got, let me pull that up. So we have a, so we're given the grams of silver nitrate, and we're given grams of copper 2 chloride dihydrate. All right, and to calculate theoretical yield, when you have 2 starting quantities, you have to do the theoretical yield calculation twice, and then whichever one comes out smaller, the smaller of the 2 is your theoretical yield, and it is given to you by your limiting reagent. So the setup here is we got to do this calculation for both silver nitrate and copper 2 chloride dihydrate. So first we use the molecular weight for silver nitrate, and then to convert grams to moles. Then we convert moles of silver nitrate to moles of silver chloride. And these molar ratios come from the chemical equation, right? The balanced chemical equation. Finally, you use the molar mass of silver chloride to convert from moles of silver chloride to grams. All right, and that gives you one possible answer. You repeat the same calculation down here. You start by converting grams of copper 2 chloride dihydrate to moles of copper 2 chloride dihydrates. Then you convert from moles of our copper 2 chloride dihydrate to moles of silver chloride. And again, this molar ratio comes from the chemical equation. All right, then your last step, we convert from moles of silver chloride to grams. And this will give us another possible answer. So then, once you have these two numbers, you got to compare them. The smaller value is the theoretical yield. All right. Okay, so that is how you handle question 3 of Lab 6. All right. Let's see. Okay, there we go. Okay. Oh, Karenza, don't I just now saw the comment. Sorry for making you check everything. Totally fine. Sometimes things go wrong. Like sometimes the tabulated values, which I got from another professor, generated this set of data. Sometimes they're off and they give wacky numbers. So it's totally worth checking. Let's see. Show how to do number 3. And the question's part of Lab 6. Oh, shoot. So we just did. That's useful. So this is how you do. So we just ran through that. Let's see. Do you know how to do the actual yield for number 4? I believe I do, but let me take a look at number 4. Calculate your percent yield. Okay. So let's talk about Lab 6. Oops. Lab 6, question 4. So So number 4, we're being asked to calculate our percent yield, which as we know is actual over theoretical times 100. Okay. Let's take a look. Okay, so the cool thing is we just talked about where this comes from, right? This is question 3. All right. Now the cool thing about your actual yield, this guy right here, is a data analysis data analysis 6, the whole net weight of the silver chloride precipitate. So actually, number 4 is relatively painless. That is how you handle it. You just did your theoretical yield. Your actual is just how much you actually made in this digital lab. Okay. Let's see. Okay, cool. There we go. Kate, practice homework 6, number 80, walkthrough. Yes. Let's take a look. Nice. Okay, so to do this problem, we need a balanced chemical equation, which they don't give us. So, that's a little nasty, but we can do it. So this is chapter 6. Oops. Number 80. Okay, so they are asking you are welcome. How many grams of aluminum are needed to completely react with 55 grams of sulfur? They say in the synthesis of aluminum sulfide. All right, so here to do this problem, we need a balanced chemical equation. And they don't give us one, but I'm here. I will either give you one or tell you what your reactants are. And they low-key tell us our reactants, so, but I can see how this would be confusing. So aluminum plus sulfur reacting to make aluminum sulfide is the reaction. This one isn't balanced, right? We need 2 moles of aluminum and 3 moles of sulfur on the reactant side. Now it's balanced, okay? And they tell us that we want to completely react 55.0 grams of sulfur, and they're asking us how many grams of aluminum do we need. All right, so this is the setup. Now let's crunch some numbers. So we're going to have to do some stoichiometry, right? We start with 55.0 grams of sulfur. We got to convert grams of sulfur to moles. And this unit conversion we get straight off the periodic table, 32.07. Grams is the atomic mass of sulfur. Moles of sulfur. So now we need to convert from moles of sulfur to moles of aluminum. And this unit conversion we get from our balanced chemical equation. 3 moles of sulfur react with 2 moles of aluminum. Then finally, we need to convert from moles of aluminum to grams of aluminum. And aluminum has an atomic mass of, I think, 26.98. Let me just check. Yep, 26.98. So now, grams of sulfur cancel grams of sulfur. Moles of sulfur cancel moles of sulfur. And moles of aluminum cancel grams of aluminum. So we have 55.0 divided by 32.07 times 2 divided by 3 times 26.98. So my calculator is giving me a value of 30.8471053, right? But we can only keep 3 sig figs because that's the fewest. We've got a couple other things with 4, but we got to roll with the fewest. So we keep 3, 4 rounds down. So our final answer will be 30.8 grams of aluminum are required to react with 55.0 grams of sulfur. All right. So that was a problem. That was number 80. Sorry, I couldn't remember. Let's see. Prathana, you wanted to see 85. Let's take a look. Chapter 6, number 85. If 125 grams of calcium nitride were produced from 29 grams of nitrogen and excess calcium, if they were according to this reaction, what is the percent yield? Oh, interesting question. This is a cool question. So they give us a balanced chemical equation, which is nice. 3 moles of calcium react with 1 mole of nitrogen to produce 1 mole of calcium nitride. They tell us that we start with 29.0 grams of nitrogen and excess. So that means we have enough. And then they tell us that, I'm going to quote it here, 125.5 grams of calcium nitride were produced. That means that this is an actual yield. And you'll notice they want to know what the percent yield is. Percent yield is equal to actual, which we have, over theoretical. So to solve this problem, we need to calculate our theoretical yield because they gave us our actual yield. And to do that, we have to start with the mass of nitrogen we were given, calculate our theoretical yield of calcium nitride, and then we'll be able to determine our percent yield with the actual yield that we were given. So we got grams of nitrogen under moles of nitrogen. Next, we got to convert moles of N2 to moles of calcium nitride. Finally, we convert moles of calcium nitride to grams. All right. We got a couple molecular weights to calculate. For N2, it's just two nitrogens together, right? So that's 28.02. And then for calcium nitride, we've got 3 calciums, 2 nitrogens. Calcium is 40 point something. Should not remember. So let's look at the periodic table. 40.08 times 3. 14.01 times 2. So let's see, 40.08 times 3 plus 28.02 is, wow, that's huge, 148.26. This balanced chemical equation, 1 mole of nitrogen produces 1 mole of calcium nitride, so this is a 1-to-1 ratio. So now we're ready to calculate our theoretical yield. So we got 29 divided by 28.02 times 148.26 is 153. Oh, just 153. We can only keep 3 sig figs. All right, so now we calculate our percent yield, which is actual over theoretical times 100. So actual 125.5 grams divided by theoretical 153 times 100. So we got 125.5 divided by 153 times 100, keeping 3 sig figs, is 82.0%. This is our percent yield for this reaction. All right, that's chapter 6, number 85. Okay, Esther, you've been waiting patiently. We're here. We're almost at the bottom of the comments. How do we tell if a compound contains ionic and covalent bonds? Esther, great question. Let's take a look. So let's think about this. When we're talking about an ionic bond, we're talking about the attraction. Oops. The attraction between positive and negative charges. All right. When we were talking about a covalent bond, We are talking about electrons shared between nuclei. All right. Now, there's only one way to get both of these present in the same molecule. To have both an ionic and covalent bond, you need an ionic compound. Oops. With a polyatomic ion. All right? Because, for example, like sodium nitrate, for example. If you look at the nitrate anion, oops, whoa, anion, not cation. There we go. Let me get all my lone pairs in here. All right, there's the anion, and then the positive sodium cation. It has an ionic bond because of the attraction between the positive and the negative, and it has covalent bonds because those electrons are being shared between two nuclei. So if you can identify an ionic compound with a polyatomic ion, that molecule will have both ionic bonds and covalent bonds. So that is what you're looking for if you're looking for a molecule with both. Alrighty. So, as of right now, I've hit every question in the comments, and I'm still here. We got another 53 minutes to hang before office hours are over. So I'm still totally here, ready for any new questions. When you got them, hit me with them. I'm going to check some emails, do some class stuff, but I'm totally interruptible. So hit me up the second. Ooh, balancing equations. Yes! Okay, thank you. Oh, man. I have a memory like a sieve sometimes. All right, let's see. Okay, you asked this question forever ago, and I totally forgot about it. Brianna, thank you for being both patient and gracious. Let's see. Oh, okay, right. A practice problem, balancing equations, where you've got to use a fraction. Okay, give me 1 second. I'm going to scribble on some scratch paper just to make sure I'm coming up with one. Let's see. I feel like this is one. Okay, yeah, here's one. So let's balance this dude. Oops. The reaction between, oops, or I should say the combustion of ethanol, which produces CO2 plus H2O. Alright, so let's balance this chemical equation. We've got carbon, hydrogen, and oxygen on both sides. Okay, so we have 2 carbon atoms, 6 hydrogen, and then our reactants side we have 1 plus 2 oxygen atoms. On the product side we have 1 carbon, 2 hydrogens, and then 2 plus 1 oxygen atoms. Alright, start with what's easy. Let's multiply CO2 by 2 to balance our carbon. This balances carbon and unfortunately unbalances oxygen in the process, but it's part of life. We are used to it. So carbon's balanced. Now let's look at hydrogen. We need 6 on our reactants, on our product side. So let's multiply H2O by 3. This will balance hydrogen, and it won't balance oxygen, it just changes it. Alright, now, here's the trick. We just have oxygen. On our reactant side, we have 1 plus 2 oxygens. On our product side, we have 4 plus 3. Now here's the deal. We are looking for something to multiply by O2, right? We don't want to mess with hydrogen. We don't want to mess with carbon. We want to multiply O2 by something so that the number of oxygens on both sides of this reaction are the same. Now we have an equation we can solve. So if we subtract 1 from both sides, we get 2 times our number of interest is equal to, let's see, we got 4 plus 3 minus 1 is equal to 6. Wait, do we not need a fraction here? Sorry, I thought we needed one. We don't. Check this out. Sorry, I'm gonna do another one where we do need a fraction. N equals 3. So we just multiply this by 3, and now we're balanced. Because 1 plus 6 is equal to 4 plus 3. Okay, hang on. I'm gonna do one where we have to use a fraction. Just give me a second. Okay, I actually have one. Okay, here we go. This one we actually need to use a fraction. Oh man, okay. Let's balance this one. Let's balance C5, H10 plus O2. This is the combustion of pentane. Produce carbon dioxide and water. Alright, CHO, CHO. On our reactant side, 5 carbons, 10 hydrogens, 2 oxygens. On the product side, 1 carbon, 2 hydrogens, 2 plus 1 oxygens. Let's get to it. We need 5 carbon atoms on our product side, so we need to multiply CO2 by 5. This balances carbon and just changes oxygen. Oxygen wasn't balanced before, so we're not shedding any tears. Next, we need 10 hydrogens on our product side. Well, we've got 2 in water, so if we had 5 water molecules, that, not times 10. That'll balance things up nicely, changes our oxygen count. But again, to 10 plus 5, it's not like it was balanced before. Okay, now I'm getting dramatic and I mean it. So we've got 2 oxygens on our reactant side. We have 15 on our product side. We need to multiply O2 by a number that's going to make these 2 sides of the equation equal. When we solve for that number, we see N is equal to 15 halves. Watch what happens when you multiply O2 by 15 over 2. 15 over 2 times 2 is 15. We're balanced because 15 is equal to 10 plus 5. All right? They're equal, but there's a problem. You can't have half of an oxygen molecule. Right? There are no scissors to cut that molecule in half so you can have half of one. They only come in whole numbers. They only come in integer units. So, we have to get rid of our denominator. The way you do that is you multiply everything in the whoa! What did I just do? Holy moly, hang on. There we go. You multiply everything in the chemical reaction by your denominator. All right? So we're going to have our final answer will be 2 molecules of pentacarbon decahydrogen plus 2 times 15 halves is 15 molecules of O2, producing 10 molecules of CO2 plus 10 molecules of H2O. So this is the final answer for our balanced chemical equation. Okay. All right, I see there's been a flurry of new questions, so let's take them one at a time. Esther, another question. How do we know when the first name of an element in a compound is not dihydrogen and hydrogen? Esther, so when you're naming covalent compounds, you always name them like this. They're always prefix atom 1 followed by prefix atom 2, ide. There's a thing in the book where it says, oh, when it's hydrogen, you don't use the prefixes. You don't have to worry about that. Just always name them the same. So, for example, this would be, so our first prefix is tri. Our second prefix is mono. So you would name this thing, whoops, not that kind of tri. Trihydrogen monoarsenide. All right, you don't have to worry about that thing it says in the book where it's like, oh, don't ever use prefixes for hydrogen. You can just use prefixes every time and you'll be fine. Just, yeah, the only time you don't use a prefix for the first atom is if there's one of them. And that's evidenced by, by this. If the first atom only has one, you don't use mono. So this would be carbon monoxide. Here, hang on one second. I'm getting a phone call from a number I don't recognize. Give me one sec. Hello? Telemarketers. Sorry for taking that. Just in case, I always answer numbers I don't recognize now in case it's like a doctor's appointment. Because turns out, if you miss an appointment, then they can't bill the insurance, so then you have to pay for it. We found this out during Rona season. So I always just check. It was a telemarketer. Okay. So this would be carbon monoxide. This would be carbon dioxide. Anytime there's only one leading atom, you drop the mono, but that's the only time you drop something. Okay, let's see. Homework for chapter 5. Let me check. Let's see. Homework for chapter 5. Oh, sorry, hang on. Let's go to Canvas. Canvas. Okay. Homework for chapter 5. Number 1 and number 2. Let me see. And then all right, Carenza, homework 4, which is on chapter 5. Problem 1 does have the correct answer. Let me check out number 2. Which of the following compounds are all the bonds single bonds? Okay. Let me see. That one's okay. This one. Yep. Okay. Okay, yeah. Those are all correct. Okay. For number 2 and homework 4, still having trouble finding the compound with all single bonds. Okay, so let me know if this clarifies things for you. Okay. So which molecule has all single bonds? Compare these two. In the first one has 2 singles and 1 double, versus the second compound only has 2 singles. That's the only type. So we would say that water has all single bonds because the single bond is the only type of bond present in the molecule. Does that make sense? It doesn't have to be a molecule like this. It doesn't have to be it doesn't have to be like methane, which looks like this. This question is simply asking you to identify a molecule where the only type of bond present is a single bond. Ah, okay. So the only molecule There's one that doesn't. There's totally one that doesn't. And if I had to guess, okay. If I had to guess, I think the reason you are coming up with a double bond on the molecule with all singles is because let's see, you may have so try taking a look at your valence electron calculations, because that may be the reason why you're coming up off. All right, now the only molecule that can have both ionic and covalent bonds is an ionic compound with at least one polyatomic ion. So that's what you're looking for when you're trying to identify a molecule that has both ionic bonds and covalent bonds. Let's see. Yes, I totally can. I can totally keep that on the board for a while. Absolutely. Yes, that is correct. Oops. You are welcome. All right, let's see. Ah. Kate, great pair of questions. You are welcome. Okay, let's see. Got a compound like N2AT. How would I... Oh, very close. Oops. You are welcome. Okay, let's see. Ah. Always subtracts. Um, You are welcome. Alrighty, well, it is 6 o'clock. I'm going to put a pin in this office hours. We're officially, as of right now, halfway done. Thanks all for coming out. I'm going to bounce because I haven't seen my baby for about, what time is it? 6? He went down. I put him down for a nap at 12, so it's been 6 hours since I've seen him. So I'm going to go see that kid, put him to bed in about an hour-ish. But thanks everybody for coming out. I hope you have an awesome 4th of July weekend. Remember, no class on Monday, so we get a 4-day weekend up in this business. And I'll catch you all on Tuesday. Later.